Consider the 48-kilogram mountain climber in the figure below. We want to find the tension in the rope and the force that the climber has to exert with her feet on the vertical rock face to remain stationary in equilibrium. We'll assume that the force is exerted parallel to her legs, and also assume negligible force exerted by the arms. Okay. Alright, so in any one of these equilibrium problems, we typically want to just redraw the situation using the free body diagram. And, it's common for me to move vectors so that their tail is at the dot. Here they've got the tail somewhere else, like not at her center of mass. So I'm going to move that vector. So I'm going to do that. This is going to be the force, which is like a cliff on foot, cliff on person. We've got some kind of tension force here, which they're calling T. And one that's not shown is her own weight, which could be something like that. And I'll just call it W. Alright, so it would be great to resolve these forces into components. So we can say, take the cliff for example. Let's create an X and a Y component for each. Alright, so we can see that that's a little out of scale, the vectors, so I'm going to correct that. Just going to shorten them up. The idea is we want balance in the X and the Y. Alright, so this one can be called Fn. So why do I call it Fn? Because normal means perpendicular. So if you look at that surface there, the component of the force of the cliff that's like 90 degrees with the cliff is a normal force. And then there's also this force which goes parallel to the cliff. That's the little blue one. That would be a friction force, FF. But it's not just any type of friction. It's a special type called FS, for a force of static friction. Alright, so the idea is that the cliff has two different types of surface forces that it entails. Alright, when it comes to the tension, we'll just have Ty, vertical tension, and then horizontal tension, Tx. Alright, we would want to sum our forces now. And we could even redraw the thing without the diagonal vectors. So we could now redraw it on the side here. So there's the weight vector. We'll have this Fs, Fn, Ty, and Tx. Alright, those are the forces that we want to sum together. And so for any equilibrium problem where someone's at rest like this, according to Newton's first law, the sum of the forces has to be 0. and that means that the sum of the forces in the x direction is 0, and the sum of the forces in the y direction is 0. So let's set up a calculation for the sum of the forces in the x. That's going to be Tx plus, I'll call it Fnx. Okay, it just means in relation to the x-axis. And we want to set that equal to 0 because that is part of the conditions of equilibrium. Over here for the sum of y, we'll have Ty plus Fsy plus Wy. And that's going to be equal to 0 as well. Now let's see if we can actually get some numbers for some of these things. They tell us her mass, so we can definitely find the magnitude of her weight. So her weight is going to be W equals mg, which is 48 kilograms times g, 470.4 newtons. So that's one thing we can plug in. So what I'm going to do then is I'm going to figure, we'd like to know how big the tension is, what's the magnitude of that, and we'd also like to know what's the magnitude of that. So what I'll do is I'll rewrite stuff. So Tx could be written as T cosine of the theta of T in standard position. And then for Fnx, I'll write, it could be the force of the cliff, F, times the cosine of the theta of that force, and we'll set that equal to 0. Now over here I'll do the same kind of thing. I'll do T sine theta of T plus, here we've got the force of static friction in the y dimension, so that's going to be the force of the cliff times the sine theta of that force. And then when it comes to her weight, we actually have a number for that. But the weight points down, so I'm going to give it a negative. But my next step would be to plug in the angles. They did give us some angles, which is nice. We'll make this T cosine of the rope angle. This is not a standard position angle though. Okay, so the vector points up and to the left, which is second quadrant. So when we measure the standard position angle, we actually want to go from the positive x direction and measure it this way. So by alternate interior angles here, this is going to be 31 and this is 90, so we're talking about 121 being the actual angle that the tension force is pointing. When it comes to the force of the cliff, 15 actually is a standard position angle. You can see it right here. That is measured with the positive x-axis. So I will use that. Alright, then we'll fill out the rest. Great, now we've got it down to 2 equations and 2 unknowns. So it should be solvable. I'll plug it into an online system of equations solver. F cos 15. So once you do the first equation, you put a semicolon, and then that separates the equations. I think that'll do it. Alright. Doesn't always give you a nice answer. Anyway, it gives you the T is 472.7. So we're looking at 473 newtons for the tension. And I'm just going to plug that into one of the formulas to find F quick here. Saying that the force on the feet would be 252 newtons. I'll just check that though. Check it with both equations. Alright, it checks in the first equation. Yeah, it looks like the second equation checks too. Alright. Now it's saying, what is the minimum coefficient of friction between her shoes and the cliff? Alright, well, we've got T equals 473 newtons. And F is 252 newtons. So if we take that magnitude of F, we could find the different components. So, for example, the normal force would have been F times cosine of 15. So that would be 252 cos 15, which is 243 newtons. And we could find the static friction force, which would be F sine 15. So 252 sine 15, 65.2. Now I find that static friction force because we actually have a formula for static friction. It's that it'll be less than or equal to a static coefficient of friction times the normal force. So luckily, it looks like we have the two things we need in order to solve for the coefficient of static friction. Plug Fs in over here. So this is how much static friction she has right now. And the normal force is pressing her feet against the cliff is apparently 243 newtons. So if we solve, I get 0.268. And the interpretation of this inequality is that the coefficient of static friction between the shoes and the cliff, it has to be large enough. It must be at least 0.268.